Yeah, we'll be starting with the next session now, and we welcome our next speaker. So before we start, we want to introduce our speaker, and I request our Professor Ganesh to give the introduction.
Yeah, good evening, everyone. I, Dr. Ganesh Archate, welcome you all for the session 8, day 4. It is my pleasure to introduce our distinguished speaker, Dr. Anbukkarasi Rajendran. Dr. Anbukkarasi Rajendran is working as assistant professor in the Department of Mechanical Materials and Aerospace Engineering at IIT Dharwad. She completed a degree from IIC Bangalore and undergraduate in metallurgy specialization from Government College of Engineering, Salem. Before joining at IIT Dharwad, she had worked for CSIR, NIST, Trivandrum, and JSW Steel for a few years. She is currently working in friction stir welding and additive manufacturing, alloy development, and materials characterization. Ma'am, we look forward to your session. The platform is now yours.
Escape to make co-host. She can share that. Yeah, just a second. We will make our speaker as a co-host. Let's go here. Yeah. Yeah, now. Yeah. Got it. Just a second. A second. I'll add a ghost. Done? Now you okay? Uh,
Yeah, ma'am, you can share your presentation. We have made you as a co-host now. Hello,
I think restriction is removed. Mute restriction. हुआ है नहीं देखो हुआ है हुआ है
Hello, ma'am. Yeah.
हाँ यार हाँ Anbu madam, please unmute yourself. Your microphone is mute.
Yeah, can you hear me? Everyone,
Voice is clear, yeah.
voice is clear, right? You can see my screen also. No?
Yeah, we can see the screen, yeah.
You can see my first page.
Yeah, first is, yeah, now it's in presentation, yeah. Just move with the slides, you will see it's moving on. Next.
Fine.
Yes.
Yeah,
Fine.
yes, it's moving,
You can?
yes, correct. Yeah, we can see, yeah.
Yeah, fine. Yeah. Before starting my presentation, let me thank the organizers for having me today here. And thanks for the wonderful introduction about me. Yes, myself, Anbukkarasi, I'm working as assistant professor in the Department of Materials and Mechanical Materials and Aerospace Engineering, IIT Dharwad. Okay, so I like to discuss about the characterization of functional materials. So functional materials will cover most of the materials. Yeah, let us get into, then we will discuss one by one. If anyone wants to get any clarification, you can stop me in between, ask me the question, or we can have the question answer session at the end. Fine? Hello?
Yes, ma'am. You are audible.
Yeah, I'm audible, right? Okay. Yes. Yeah. What is functional material? The material which is using for a particular application. So it is called functional material. Almost all the materials, yeah, some of the materials are specially used for, can you see my cursor also?
Yes, ma'am. We can see.
Yeah,
One
pointer,
second.
right? Yes.
Yeah.
Yeah, some of the materials are highly compatible to prepare or manufacture the for bio applications. Some are goes with the energy sector. Some are suitable for some other applications for coating industries, or this one is for semiconductor application, this is for aerospace application, this is for nuclear application. So all the materials cannot be used for a particular application. The material property, the behavior of the material under a particular circumference or any particular environment decides the suitability of the material. So irrespective of any materials, the materials can be classified into three categories. One is metal, second one is polymer, third one is ceramics. So the composite is the fourth category, but it is not a specified one, but it is combination of one of these two, or can be combination of all the three. So irrespective of, as I mentioned, irrespective of any field of application, uh, we have to go with one of these materials as a material for a particular application. Okay, so why we require the material characterization? Materials characterization is basically need to understand the materials in the beginning level. If I am making some component, how the component will be behaving. If I'm making a component for a particular application, how the component will obey or working in that particular application conditions, or if I am developing any alloy, so what internally happening. So everything I can understand by doing a characterization, right? So if I'm going for any component making, I supposed to do the quality checking. Even alloy making also requires the quality checking, right? So majorly it is coming from understanding the internal structure, right? So these structures are directly related to the mechanical properties. So how I can correlate this property with the mechanical property and how it performs under the service conditions. So all the information I can get from, if I'm understanding the structure of the material clearly, I can predict the properties. By predicting the properties, I can able to say how long the material can sustain under the service conditions, right? So everything coming related to the structure. So the structure, how I can study by using the materials characterization. Right. So the materials characterization techniques can be majorly grouping or classified into two categories. One is a destructive analysis, second one is non-destructive analysis. Destructive analysis, from the name we can come to, or we can understand that the analysis part, we will destruct the material. So we have to cut and do some of the preparation for taking the sample for the analysis. Non-destructive analysis, as the name indicates, we need not to cut or anything for doing the analysis. Anyway, I'll explain how the destructive is coming for the analysis under this category, how the non-destructive without cutting or without sample preparation, how it works for non-destructive analysis, right? So the destructive analysis mainly will do under this category. The microstructural analysis is one of the analysis part, and second one is the mechanical testing. So the microstructural studies we can do by using the help of some of the characterization tools. So the characterization tools, you might have heard about it, optical microscope, SEM and TEM, and another one is XRD. Okay, so we will discuss one by one. Yeah. So irrespective of any technique, if I'm choosing for studying or understanding the internal microstructure, I need to go for sample preparation. Sample preparation is very must for doing any characterization analysis, especially the destructive microstructure analysis, right? Uh, if my sample preparation is too good, my 90% structure on analysis part will be very clear, or I can get the result of 90% if my sample preparation is well and good. Okay, so this is one of the nice flowchart I have taken from Google. So it is representing from the beginning of sample preparation to the end stage of the analysis. So first we have to start with the cutting process. If my sample is little huge, the sample size should fit into my characterization tool. Here I have given optical, so same way SEM or TM, whatever the characterization tool I am choosing, I must go with the sample size which can fit into the machine, right? So for that, I have to go for the cutting process initially. Um, the cutting process also how I can choose based on the region or any particular area of interest I am looking from the bulk component. I have to select first and which of the cutting device will not destroy the feature of it. I have to keep everything in my mind before going for cutting. So once I have cut, if the before cutting, if the sample size is too smaller, I need not to go for the cutting process. I can skip it. Either small sample or larger sample. Once I am bring to the sample size which is fit to the machine, then I have to prepare it. That is the very crucial part in the characterization technique. That is polishing. So polishing is must. Why? Because our analysis can be aided by optical rays or electron rays. These rays must not get be distracted by the surface burst by introduced by the external thing as well as the cutting process, right? So this polishing steps only is, as I mentioned, very crucial. It is an art. We have to take care very precisely. We have to prepare our sample by following each step. If my sample is too smaller, I can mount it with the help of one of the resin which is fit for the particular sample. At the same time, I have to ensure that this also should not damage the sample or it should not undergo any reaction during analysis if it is polymer. Okay, so these are the things I have to keep in mind. I have to mount the sample, then I have to go for the polishing. Polishing, I can divide into multiple categories from coarser to finer. So in that step, mainly I am bringing down whatever the scratches introduced during cutting or external thing. I am bringing down from coarser to very micron level, which will not be hide the internal features when I am taking the sample to analysis under the microscope. Okay, so all the procedure after that, I can take the sample to the microscope for the analysis. Um, so I have given, you might have seen in your lab, this is the very basic and very easiest tool for seeing the microstructure. Okay, so and most of the details we can get from optical microscope. So then this is SEM. You might have seen some of you might have used also or familiar with this, right? So for it has a special purpose. Then for analyzing for doing the analysis of any particular or any particular anyone raise any question? Any disturbance? Hello.
No,
Hello.
madam. No, madam. No questions. Continue.
I can proceed.
Yeah.
Okay, fine. So based on some particular application, I can move to SEM. Everything I'll point out in the coming slide. Okay, so this is one of the micrograph of functionally graded material. The functionally graded material developed by directional solidification. We are aware of it. The directional solidification is one of the casting process. So I'm not getting into how the process will be done, but this is one of the casting method. Due to the directional solidification, by controlling the cooling rate, they have developed the gradient in the microstructure. The functionally gradient word can fit to anything. So the gradient can be in terms of microstructure, in terms of composition, in terms of mechanical properties. Okay, so anything, whatever I mentioned, if it is varying from one end to another end, it is represented by the word of functionally graded. Okay, so this is one of the functionally graded material, the gradient in its microstructure. Okay, so this microstructure around the, see, you can see the length, the entire length we can see it is possibly by optical microscope only. Okay, so no other characterization tool help to see the complete or the maximum area of samples can be analyzed. So that is one of the major advantage of optical microscope. And even optical microscope also have some restriction in size. So this is in that case you can go for montage, like a continuous microstructure you can take and stitch it. Then you can see the overall variation or gradient in the microstructure. You can get the feel how the variation in the microstructure by doing these kind of stitching images, right? So then if we have any particular region of interest to have look into the microstructure, then I can select the region, bring the particular portion and exactly to the where the optical beam is falling. So then I can try to analyze or evaluate what is the structure is present in that particular location, right? So as I mentioned, sample preparation is important. After the fine polishing, some samples are required one more additional procedure that is called etching. Some of the features does not require etching process. Some of the features like whatever precipitates or the cast structure, the dendrites with more alloying elements may not require the additional procedure that is called etching. Etching is mainly helpful to reveal the grain boundaries. So you need not to go for etching for all the samples. At the same time, all the samples cannot be analyzed without etching also in as polished condition also. This is only direct polishing. After polishing, these needles can be seen. So this we have not used the etching for revealing any internal structure. Okay. This is one of the structure from the additive manufacturing deposited layer. But in this case, the etching procedure is required. Etching is selectively uh, attacking by the chemical, the grain boundary or special features will be attacked by the selective chemicals. Each material or each metal will have its own chemical for doing the etching process. We cannot use a common etchant for all the samples. Okay, the etching process, the chemical which is used for etching process is called etchant. Etchant is the combination of multiple acids, so that cannot be same for all the materials. So you have to select the etchant for each material, the specific etchant you have to go for. Okay, so this microstructure representing of the 3D printing, as I mentioned. So in first case, they have developed the printing part from down to up, that is along the x-axis. Second one is along the y-axis. Okay. So third one is the alternating layer, x-axis, y-axis, x-axis, y-axis. Fourth one is one x-axis, y-axis, x-axis, one rotational. First x-axis, then rotate, then do the deposition part. So this is basically for properties, as I mentioned, the internal microstructure directly related to the properties. So to achieve certain properties, the author might have done such a variation in the deposition printing thing. Okay, so after printing, how the deposition layer or internal microstructures are there. So they have cut the sample, prepared the procedure, whatever I mentioned, then they have used the suitable etcher, then these micrographs taken under optical microscope. Okay, so this is another alloy. So that is done by my student at IIT Dharwad. So this is also additive manufacturing part. As I mentioned, once you looked into the deposition layer, even at the interface, how the variation is there in the deposition or orientation in the grains, that can be revealed by zooming in a particular area. So this is another micrograph from the dissimilar metal welding, which this was done by myself for my postdoctoral research. Okay, so again, it is a montage image of the interface, weld interface, right? It contains nearly 100 small micrographs, optical micrographs. So then our interested region, we focus, we taken at high magnification. So it reveals the grains clearly. Some region fine grains close to, this is the weldment, close to the weldment, there are coarser grains due to heat affected burn. Whereas other side, there is no heat affected zone, such coarser grains we are not seeing here, as both the weldment and the base metal are same material, right? So the dendritic growth in the weldment also is seen clearly. So as I mentioned, most of the information we can get from the optical micrograph. If our sample preparation is good, we can get the complete idea of microstructure from the optical micrographs itself. Okay, so optical micrograph can give another information, like this is one of the corrosion sample which I have carried the corrosion test for one of the DST project. Okay, so after it exposed to certain temperature at different pressure, so I could see some layers formed at the surface. So I wanted to see first under microscope. So the microscope, these numbers are showing the time of exposure, the sample at the particular environment. So with increasing temperature, the layer thickness gradually increasing. So the message from this image is, yes, optical micrographs can be, or optical micro scope can be used to reveal the coating also, and you can measure the size of the coating. This image taken in as polished condition. It may not require any etching process, as the coating material is different from the base metal. The contrast difference can help to reveal the coating clearly. Okay, so whatever the things we are seeing at optical microscope, some features, if it is finer, we cannot make clearly in optical microscope. In such a cases, we need to go for a help of another tool which can zoom little, magnifying it, and which can reveal the features clearly. So scanning electron microscope is one of the tool which can magnify the features up to 2 lakh times from its original size, right? So this is one of the micrographs from the multi-phase steel, ferrite, martensite, some of the bayonites are here. So it cannot be clearly revealed by optical microscope. So with the help of STM, we try to distinguish the phases and confirm the phases present in the sample. In addition, SEM micrograph can be used to reveal any cracks or any defects are present. So SEM can be used. Again, these analysis required the standard sample procedure, what I mentioned for optical. Same thing we have to follow. And the etching, these are all after etching, under etched condition. So to reveal the feature, we supposed to do the etching. If I want to see the crack propagation, whether it is along the grain boundary or through the grain, so to understand the crack propagation, I must do the etching process in the cracked sample. And if in case of any features like precipitates are present, where it is presenting, whether along the grain boundary or within the phase, all the details I can get if I'll do the etching process. Okay, so this is some of the precipitates in the sample. This is one of the nickel sample which is having the gamma phase and carbide phases. Okay, so just I'm looking into the precipitates, I need not to go for etching. As I mentioned again, if I want to see the location, I need the etching process. This is another sample where alumina embedded into aluminum matrix. So to reveal how the alumina distribution in the matrix, we prepare the sample and we try to understand the distribution of particles under SEM. So some places it's not mixed properly, there is agglomeration. So these information also we can get from SEM. So it may not require the etching process, but as I mentioned, the polishing is must. Same way, this is some of the polymer. So how the procedure we are following for metallic sample, the polishing, paper polishing, etching, other thing. The polymer sample, we may not, it may not require the polishing procedure. Okay, so as it is, you can take, but if it is charging material, like a non-conducting material, it's supposed to be coated with the conductive material like gold. So before taking into my SEM machine, you must do the gold coating over it. That is a conductive coating to avoid the charging of the sample. Okay, so yes, we can do the analysis of polymer. And in addition to analysis, how the embedded of one polymer into the matrix, uh, by using SEM, we can measure the size of the particles also, fiber. Okay, same way, this is another feature in one of the matrix. Okay, so the size also is measured by using SEM. So top of that, if I want to understand the what particle it is, I want to do the analysis. I can see the particle is present in the matrix, but I'm not aware what particle it could have been. So that I have to go for another additional support that is called EDS detector. This detector is embedded with the SEM. Okay, so the machine as it is will be with backscatter electron and the secondary electron sources that will be used only for the imaging purpose. If any additional information you want, you have to go for an additional detector. So for analyzing the chemical composition, it is required EDS detector. Okay, with the help of that, you can select the region, do the analysis. The detector can help you to find out the composition of the particle. Okay, so that is the case of particle. If it is a layer, this is the coating, what I showed in the optical, the same sample we have seen under SEM also. There are two layers. So I am interested in finding the composition of both. So I have selected the particular location. I did the point analysis. Okay. So in EDS analysis, either I can go as a point or some area I can select, or throughout some line also I can select. I can show some of the examples in the coming slides. Okay. So here I have selected some particular spot. Okay. To understand the thing. So it showed the variation in the composition. As I mentioned, if the here it's a metallic, it's a coating, have a uniform composition throughout the layer. Only there is a composition variation between the layers. But here within the layer itself, there are multi phases due to the different composition and the way of coating. Okay, so I have to select each region to understand what are the phases it could have been. Okay, so this is the point analysis. Even I can select a area of this entire phase. So area analysis also I can carry out. As I mentioned, this is line scanning. If there is a gradient, okay, so I can choose from one end to another end. So how the variation in composition that can be studied by using the line analysis using the same detector. So the same detector provide me the information of the composition from one point location, some area, or if I am giving as a line, so the entire region. In line, if I am giving a multiple points, from each point it will pick, it will give us a graph. Okay, so again SEM can be used for doing the fractography. This is one of the polymer sample, the fractured surface under SEM, it shows the fracture propagation, right? So if I am doing for the metallic samples, as we are familiar, the metallic samples can show the ductile fracture and brittle fracture. So the ductile fracture, ductile mode of fracture can be understood from the way of fracturing. It is a dimple, presence of dimples in the fractured surface. The presence of a flat surface shows the brittle fracture. Okay, so yes, along with the SEM, addition of eBSD tool can give an additional information about the grain size distribution, even presence of stress, grain orientation, many things we can analyze. So this is one of the 3D printed part looked for the grain size distribution. Okay, so by using the EBST technique. So these are the similar or corresponding image what I showed for the optical analysis. So one is the printing along x-axis, another is printing along y-axis. One more thing is like alternate, another fourth one is the rotation way. So all the different way of printing, how it affects the internal grind, right? So later when we'll do the mechanical properties, we can come to know that the internal microstructural changes, how it affects. Okay, so EBST serves the purpose of grind size, analyzing the grind size distribution as well as the orientation. So this is one of the sample, dissimilar weld sample, what I showed in optical, the same sample in the dissimilar side. This is nickel side, this is 304 side, and this is the heat affected zone where the coarser grinds are seen. So the weldment shown with the dendritic grinds, coarser in size, very huge grain size we can see in the weldment, and heat affected zone are coarser than the base metal. So this is the typical base metal, so which is having the very finer grain size. Okay, so this is another weld sample by friction stir welding, copper and aluminium. So multiple zones, you know that during friction stir processing or welding, it will be developed. So zone wise, how the grain size variation is, so that we could able to study by using EBSC analysis. So this is one of the another technique. It's not related to SEM. It is a separate technique. Just to show the region I included here. This is called extrude tomography analysis. See here the copper part other side, it is hidden here. So it is welded with aluminum by friction stir welding. So during welding, you could see some of the fine particles of copper distributed in aluminum. So how this distribution has kept is that the size and distribution of this base metal into the second matrix material, we could able to see by using the tomography technique. It requires a special sample preparation. There is a restriction of thickness to make this 3D images. Nearly 1 mm or 2 mm. So you have to slice your sample into that size, and both the sides, some rough polishing. Need not to have a mirror image polishing, final polishing. Some rough paper polishing would be sufficient. Then you can place the sample in the machine. So by using X-ray source, it will do the mapping and it will give the 3D image of that. We can get the information completely about the particle distribution in the matrix. Then along with SEM, there is another detector that is called WDS detector. It is wavelength dispersive spectroscopy detector. Okay, so I think I missed to include EDS mapping there. So EDS mapping can give you whether any enrichment of phases is there or not. If there is some enrichment phase, it will give some bright appearance. If it is not there, there won't be anything. But WDS enables the gradient. However, what are the if from one region to another region, if there are any gradients in the composition, everything can be covered, and the composition, it will be highlighted by a different color with respect to the concentration variation. Okay, so this is by using the WDS detector, again the composition variation across uh, this layer, top layer. Actually this layer is formed by corrosion. So this is the corrosion product. Okay, so when I am doing the line mapping from one side to another side, okay, so the variation in the composition given me the idea of the diffusion, how it happens from one side to another. Okay, I think my XRD. sorry, this is not working. Let me pick another. Okay. Okay, I'll show you. Okay. I just opened, somehow I missed. It's not seen. XRD is another tool which is working with the principle of Bragg's law. You might have known this. So for XRD analysis, you need not to do the sample preparation like what we are doing for the analysis, whatever we are doing under SEM. Same way you need not to go for XRD. So any bulk sample you can take it for analysis. Only some rough preparation like a paper polishing only you have to do. So the advantage of XRD is, before pointing out the advantage, what are the informations you can get, any phases are present, and crystal structure, this lattice parameter, I don't want to go into very deep, very specific parameters and all. So whatever it will be useful for you, I'll tell just to identify any new phases are present in the system. So the phase analysis is nothing but similar to the composition analysis, like this. So similar to EDS, EDS can give only the composition of each phase, so each element. How much zinc is present, how much magnesium is present. For example, if I'm taking here, I'm doing EDS analysis, how much zinc is there, how much magnesium is there, how much aluminum is there, it will give. But as a combination, what could be the type of precipitate, I may not get to know. So that information XRD will give. So whether it is a ZN, 2mg, AL6, like that, the exact precipitate phase can be, the information of that we can get by using XRD. Okay, but the disadvantage of XRD is, here I'm seeing the place. Okay, so from where I'm taking this, I can come to know. But in XRD, we will place the sample, we don't know from where the peak is coming out. So we cannot locate the precipitate, but we can identify the precipitate and we can understand the presence of precipitate in the system. Okay, so that one. So whatever we discussed is one of the destructive analysis, that is microstructural analysis. The second one under the destructive analysis is the mechanical testing. So mechanical testing, again, it's one of the characterization which is helpful to understand the properties, mechanical properties of the material, right? So there are a number of tests are there, but mainly we will use harness test and tensile test. The rest of the test serves a particular purposes. So based on the purpose, we will select one of the tests. Again, mechanical testing, each test requires its own sample preparation. So ASM standards are available, how to go for the sample preparation for each test. Okay, so according to that, we have to prepare the sample, standard samples, then we can execute the test. Okay, so again, yes, samples, any plates if you have, or any samples you are taking from casting condition or rolled condition, irrespective of any manufacturing technique, or if you are going for a 3D printing sample also, the orientation or the direction from which you are preparing the sample matters, uh, how you are getting the results. So with respect to the orientation within the sample, the results may vary from longitudinal transfer, cross-sectional directions may give the variation in the property, right? Ultimately, you know the standard sample preparation. I'm not getting into that. Okay, so after the standard sample preparation, we will fix the sample in UTM machine. So as a mechanical engineer or the basic whoever using the sorry, if more other than mechanical engineers are there, just excuse me. You might have used, other people also might have used UTM machine, right? So you may know um, how to fix the sample, how to perform the test. So I'm not going to show that. So this is one of the standard sample. You will fix it. You will apply the load till fracture, right? So finally, we will get a stress strain curve from the machine, right? Machine may give, but it may have the information from the material, right? So the material, this information from a stress strain curve, we can get the mechanical property of yield point, UTM, and uh, the stress required to fracture the sample, right? So from the graph, it will give how much percentage of ductility a sample can have and the toughness. So yeah, the area under the curve will give you the toughness. So the sample, how stronger, how tougher, it is. It can give a better ductility. All the information you can get from this test. I think this image also is missing. Okay. So yes, next test is hardness test. Harness test also most of mechanical engineer or materials engineers we will have in our lab. Okay, this is also one of the very basic and important destructive characterization technique for analyzing the mechanical property, right? So harness is nothing but a resistance to the indentation. So based on my samples quality, the resistance will come out. Okay, so harness in background, how the harness, the machine is giving the harness number is, I'll be applying some standard load. Okay, so based on the material softness or hardness, my indentation will be made on the sample. So load by area will give the hardness value, area of the indentation, right? If it is a too hard sample, area will be lesser. So I'll end up with the high hardness number. If soft sample, my area of indentation will be larger at a constant load. Okay, so then I'll end up with the less hardness number. So high hardness number indicates the material is stronger, and less hardness number, small number, shows that the material is softer. So these are the different types of hardness machine uh, are being used for measure the hardness. So Brinell hardness machine, again the indenter will be ball indenter, right? So the indenter size also large, around 10 mm. So Rockwell also will have the ball indenter as well as the a diamond indenter, sorry, what is it, noob shape indenter also we will have, but still the load applying in Rockwell will be different from Brinell, right? So here if you are using a 10 kg kind of thing, here you will use 1 kg, 3 kg, 5 kg. Like that, the load will be lesser. So compared to this, here your sample size or sample um, selection will be different. Okay, I'll get into that. Vickers again, where the load will be used even smaller than this, right? Again, it will serve the different purpose. Again, if the sample size is very smaller, I can go for Vickers. Not only smaller sample, if sample has any special features are there, I cannot go for the larger load, larger size indenter, because my load will be acting apart from the feature. So I'll end up with the wrong result. Okay, so in that special cases, I have to go for one of these two, either Vickers or micro Vickers. Micro Vickers, especially for very tiny features, anything is there, or multi-phase structure is there. So I can go for micro Vickers analysis if my interest is to measure the hardness of each individual phases. So these are the machines you might have seen, Rockwell Vickers and micro Vickers. Yeah, this is the one of the image from micro wicker. I didn't have any images. I have not picked for Brunel or Rockburn. Okay, so as I said, if the sample is having a um, smaller feature like a grain size here, you can see very smaller, as well as it has some multi-phase. Okay, ferrite and pearlite, it is a typical pearlite, ferrite and pearlite structure. Here you can see a single phase structure. So in this case, you need not to bother where you are taking the indentation, but in this case, it does matter if you are covering majorly pearlite portion or majorly ferrite portion. That will make a difference in your final result. So that I have to go for low load, then I have to concentrate my indentation to be fall within a particular region if I am interested to measure the hardness of the particular thing. Okay, so another one is there. Okay, so that is a nano indentation. Even where a smaller load than load we are using in Vickers harness, we can use that will help to avoid the falling the load um, between multiple phases. Okay, so that nano indentation will form a very tiny indentation. So if I want to measure any fine feature, I can go for nano indentation rather than the micro Vickers. Okay, so this is non-destructive testing. As I mentioned, the name indicates non-destructive. It does not require any cutting, polishing, or special sample preparation procedure. Okay, so why it is important, where it is important. If I'm making some component, okay, I have ended up with the final product making, right? After once I made the product, I cannot go cut and prepare the sample and see whether it is fine or not. So internal quality checking or any defective, any presence of any defects inside the material, I cannot do the destructive analysis. So to understand that, I can choose one of the non-destructive testing. Okay, so this is again very basic and very simple non-destructive testing, that is a type dye penetration technique. So this dye penetration technique helps to find out the surface flaws. If there is any opening on the surfaces, so what we can do, um, you can apply the dye, right? So the dye will go and sit inside the defective region. Later, you can clean the surface completely, but the entrapped dye inside the defect will remain there. So you have to apply some developer top of that. So the developer can absorb the dyes from the defective region. Okay, so then that will, from the developer, we can come to know that where the defects are. Okay, so this is another method. Okay, before going to the next one, the disadvantage of this technique is restricted to the analysis the surface flaws. So it cannot helpful for detecting the internal flaws. So yeah, surface flaws can be identified this, but in case of presence of internal flaws, we have to select another suitable technique. This is one of the non-destructive techniques to analyze the internal cracks. Even surface cracks also can be analyzed, but the limitation or disadvantage of this is only applicable for the ferrous samples, which is having the magnetic property. So again, where the defect is there, if you pass the current, okay, so where the flaws are there, local magnetic field, there is a variation in the magnetic field you can see. So by using the suitable detector, we can see where the loss in magnetic field can be seen. So that will helpful to identify the cracks, internal cracks. So this is one of the most and common technique still now we are using or applying for any material any size, anywhere, underground water, even not underground water. So a pipeline, from small samples to larger samples, we can detect the internal flaws by using the radiography, right? So the radiography technique, again, you will pass the radiation. Okay, other side the receiver will be there. So wherever the defect is there, your radiation will be affected, or the strength of the radiation will be different. So the other side receiver will show where the internal defects are. Okay, so this is the film. You may same. It will work the same technique how we are doing the x-rays for our bones. If any fracture is there, we will go for scanning, right? So x-ray for our body, if any crack or any problem in our body, so the x-ray, how we are in medical checkup, we will do the x-ray analysis for seeing the internal. Same thing we will be using for analyze or identifying the defects even in the metal, but the radiation level will be different. Okay, so yeah, I'll stop here. If you have any, we can have a question answer session.
Any participants want to ask anything? Yeah, any questions?
Yeah, by the time I can pick some of the X,
Yeah.
uh,
In-
X or D peaks if I'm having. So many sounds I heard. Can you see this slide?
Yeah, yeah. Right,
Yeah,
sir.
this
Yeah.
is this is one of the results from corrosion tested sample, XRD results from corrosion tested sample. So the sample we have loaded into XRD machine. The machine basically will give you the 2 theta value. So as I said, this technique working with the principle of a Bragg's law. So whatever the rays coming out or diffracted rays are coming out from the sample, the machine will collect the 2 theta diffracted um, 2 theta value from the diffracted rays, and we can get the values. We need a special tool for plotting and analyzing from the 2 theta value. Okay, so expect high score is the tool that will help you to plot and identify the intermetallics. So the tool with the available with the database. So each 2 theta value based on the material. So what I skipped there, the lattice parameter A and D. Okay, so A and D, each material will have its own the theta value. So that will the database generated by using that lattice parameter. So our plot, it will be matched with the database, and we can identify the new phases, any new material. Okay, if you want to know the crystal structure, grain size, even presence of stress. Okay, so if there is a grain size variation in the same material, so that will give a different shape in the peak. And if there is a presence of stress, again that will give a broadening in the peak. So you can calculate these or you can get all this information by using the XRD. And one more thing I missed to point out in EBST, yes, the stress presence of stress. Yeah, few points I thought of covering it. Yeah, presence of stress, even you can see from the EBST graph. You can see this EBST results, right? Hello.
Yeah. EVST this. Slide number 25.
Yes,
Visible.
correct. Yes. So if you see each grain, see this is the grain. You can see the gradient in the color. So it indicates sometimes it indicates the subgrain also, but if you have a really stress in it, that can be also represented within the grains. The gradient will get the information about the presence of stress. The information of presence of stress even you can get from the EBSC analysis. So XRD also will give you the stress presence in the component that can be studied. And one more point I wanted to mention. Yesterday during Ajay's presentation, someone asked for finding out the shear strength or
Was it micro?
bonding
Yeah.
strength of
Yes.
some coating, right? If I'm correct, there was uh, okay, micro tensile one thing, and second thing is some interface layer was there. They wanted to test the strength of the interface layer, right? Okay. So that's what I understood. So the interface strength, if you want to measure again, you can try to go for the peel-off test. Okay, if there is a clear bonding between these two, if it is not developed internally, so the gradient material can be developed gradually from one material to another material, or you can join together externally, right? So if it is developed or continuous from one system to another system, like how I showed in the casting, yeah. So if it is developed, there is a smooth interface gradient, smooth gradient variation in the composition, then you can go for direct tensile testing method. I have included a few tensile things that is missing from the slide. Micro tensile also I have included. Okay, so you can prepare the sample in this direction vertically, or each this individual region, if you want to measure the strength of individual region, you can measure, prepare your sample horizontally. Okay, so if my interest to measure the strength of this particular phase, I can prepare the sample horizontally. If I want to measure the strength across the interface, I can prepare the sample vertically. So ensure that your interface fall at the interface, sorry, at the middle of the standard sample. Then you do the test, so you can come to know the strength of your interface. Okay, so if it is too thin, you can go for bend test also. Okay, so bend test, if you try to bend it, if bend test, and I whether I have included the compression test, let me check. So if you do compression test, prepare a block, try to keep your interface at the middle, then you apply the load from the top. If your interface is stronger, I think compression I need to include. So, but you might have familiar with the compression test. So you take a block, ensure the interface is falling at the middle, apply the load. If interface is strong enough, there won't be any crack initiation provocation from the interface. Otherwise, interface will fail. So that you can, there you can come to know that whether you have a strong interface or not. Okay, so these are the simple things you can do. There are many other techniques. Scratch test is there. So many. So based on these are the techniques. What very basic technique we will do. Other than that, different techniques will serve the different purposes. Based on the purpose, we can go for or select for the particular test. So shall we get into question answer session?
Yeah. Now the platform is open for questions. I think there are few questions in the chat box.
Yes.
Yeah. Okay, I'll read out few.
Yes.
Okay, Manjunath Rawat, can we get the? Yeah, we are uploading all the sessions on our institute website, and the links will be shared with you all for all the sessions. Yeah. Okay. Just a second. I'll remove the mute restriction now. Yeah, if anyone has the question, they can ask, and then we'll come to the chat box question. Yeah, we have removed the mute restriction. Please check. Please check mute restriction has been removed.
Hi, madam. Good evening.
Yeah, good evening. Please tell me.
It was a very nice presentation, ma'am.
Thank you.
Ma'am, actually, I have I am the one who texted in the chat box. Actually, is there any facilities or any central facilities for the outsiders to do the mechanical characterizations in IIT or AIC or NIT case, madam?
Yes, we have a central facility open for outsiders on payment basis. SEM,
Yes,
UTM,
ma'am.
AFM, everything is available for the
So, what is
outsiders.
the channel, madam? Channel we need to approach.
Actually, there is, in our website there is link for SAIF. Okay,
Yes.
SEIF.
Come again, madam.
Sophisticated Center for
Yes.
Instrument Facility. SCIF. I can open it.
Okay.
You can see my window, right?
Yes, ma'am.
Yeah.
It is not opening right now. Okay. You're texting. Yes. Okay. What about other IITs, ma'am? It's Dharwad is a little far away for us. What about any
No,
other
all
IITs?
the IITs, including IISc, some of the R&D institutes, they are providing facility for outsiders. So testing facility on payment basis. All the information will be available in their website if really they are offering the testing facility.
Okay, ma'am.
You can get the information from their website. All the websites are updated up to date. So
Sure,
you can get most of the information will be available.
Okay. Thank you, ma'am. Thank you.
Thank you. Next question.
Yeah. You can unmute yourself and ask the questions before we go to the chat box question. Participants can unmute and ask the questions. Okay. Shivalingayam is having one question. He is put in the text box. Like here, in Belgaum, is there any testing facilities for because hardness test are nearby?
Yeah, we have. So you can come and use. Okay. So you are welcome to use our facility. So some of the facility I mentioned in the slides also. So yeah.
Ma'am, what may be the cost of the micro wicker hardness, ma'am?
It will be very cheap only, some 200 rupees, 300 rupees.
For
That
sample, ma'am.
cost is available in the, So see, external using user booking information request form. If you have very few samples, you can write a mail to me and
Yes.
to try to reach out us.
Madam, one more that under composite vertical flammability test is there, ma'am?
Vertical flammability, sorry, we do not have that.
And another, ma'am, water absorption test, ma'am?
Even water absorption also, I have to check in another department. So in mechanical department, it is not there.
It is not
Let
there,
me check in.
Okay, ma'am. Regarding micro hardness, I will visit, ma'am. Please drop your email ID, please.
Sure. It's supposed to be available in the browser. Otherwise, from the organizer, you can take our website. In website from IIT Dharwad website, you can reach out.
Okay, ma'am. Definitely we will visit. Thank you, ma'am.
Yeah, sure. Thank you.
Amit Dixit. He had raised that. Amit Dixit. Devaraju GP. Okay. Yeah, Anbu madam.
Please.
Yeah, there was in EBSD. Can you just open your slide where EBSD was shown?
Two things I have showed you. So
WDS.
Additive manufacturing printer or
No, WDS. Sorry, WDS.
WDS. Yes.
First first file. Yeah. In this slide, EPMA, you did not, it's a part of this, or
Correct,
can you
correct.
mention?
Actually, okay, WDS analysis, EPMA analysis is done by using the detector. WDS analysis is nothing but EPMA. So another name of using indicate the WDS analysis is EPMA, electron probe micro analysis.
Yeah. Can you shed some light again on this, like this part? Yeah,
Yes.
in brief.
So yeah, the EDS is energy dispersive analysis. So what we have discussed here, which is used for measuring the composition in a particular location as a point or area or line also, right? Same thing can be done by using the WDS um, spectroscopy. Actually, EDS is energy is collected from the EDS detector will collect the information in the form of energy. So generally, whatever the interacted electrons will uh, emit the shall I go into deep? Like electrons again, diffracted rays will come in the form of photons as well as the energy. Okay, so one of the detector will collect the rays in the form of energy, another one is will collect in the form of wavelength. Okay, so the EDS detector will collect the energy form of the diffracted rays. WDS will receive the rays in the form of wavelength. Okay, from the interacted rays. So it will give more accurate result than EDS. Then the energy wave, the wavelength, energy form of electrons. Other than that, the wavelength form of electrons will give more accurate result. Okay, so this is the concept of uh, how the images are developing from the machine. If you want any information regarding how this will be developed, the gradient or mapping, this is called mapping. This is called line scanning. You want this analysis information, or you want how it works? What kind of information you want? Professor Vinay?
Mapping. Yeah, mapping.
Mapping. So this is again wavelength mapping. Same kind of similar mapping can be developed by EDS also. The energy, whatever the information is coming from the sample. So again, the same kind of mapping can be uh, plotted by using EDS. This is a WDS of the coated. It is a corrosion layer basically. The highlighted layer, this is red color, right? So the red color has a certain concentration, and this is a green color. Green color has another concentration. Okay, so I plotted this for finding out the distribution of oxygen. So each plot can be plotted for a particular element. This is the oxygen distribution in the selected area. So this dark blue is indication of absence of O in this particular region. So that is my base metal. So when I am going up from the base metal to, can you see my cursor?
Yes.
Yeah. So when I'm going from down to up, my oxygen concentration is varying from this region to here. Basically, it is an iron sample exposed to the environment. It is a corrosion product of iron oxide. So the concentration of oxide will be increasing from um, base metal interior inside to top, because the top will be in more contact, right? So the concentration of oxygen is higher at the top, and the oxygen diffusion is coming from the top layer to the inner layer. So you can see the gradient or variation in the oxygen from the top to bottom. So that gradient I can see by using the mapping of this.
Yeah. Any question?
Are you clear? Okay. So another thing I mentioned that, yeah, this mapping should be plotted for a particular element. So the particular element distribution in the selected area can be studied by using this, right? So the concentration of that particular element distribution within the selected area can be given by this color code. So color code indication from 0 to the highest. Okay, so this is plotted for iron. So here my concentration is higher in this region because it is a base metal, steel metal. The concentration of iron is depleted here because it is a corrosion product. Okay, so other side, it is a corrosion product, iron oxide. So concentration of oxygen I can see here. There is no oxygen in the base metal side. So like that we have to interpret this.
One question for the benefit of the audience,
Yes.
because characterization is like they have to use it, whoever is in materials field. Any sources for reference reading, any videos, any source can you suggest to the audience?
There is a standard ASTM volume is available. So where, that will give you enormous details or very detailed information you can get each and everything, how you have to go for, how to proceed, all the information, whatever I discussed so far, from the sample preparation, sample cutting, the cutting also at what direction it's supposed to be. Everything is given clearly in that ASTM volume. So that volume, especially for metallography analysis, that will be very useful for anyone really interested in the characterization, particularly microstructure analysis. That will be the very useful guide for following all the
Volume
steps
number,
and
ma'am,
get the better
17.
microstructure. I think volume 9 is metallography book. 9 or 17, I'm not sure. I think to my, sorry, but yes.
Yeah, including apart from microstructure, all these SEM based and X-ray diffraction, including all, or only for optical or and SEM in that line.
That is only for microstructural aspects. By from which tool we can get the microstructural information, that will be available. Actually, XRD generally it won't give the microstructural details, right? Only XRD can give the hidden details, not like revealed details. Hidden detail means crystal structure we cannot see by SEM or optical, but that detail we can get by XRD. All the lattice parameter that cannot be seen in microstructure, but XRD can give. Again, a precipitate we can see by SEM or optical, but what kind of precipitate? The compound. As I mentioned, the compound can be um, received from XRD. I think XRD is not covered in that. But other sample, it is especially for metallography. Metallography is meant for microstructural analysis. So XRD is not for microstructural analysis.
Including
Microstructure, I mean,
including EBSD part.
I think
EBSD.
EBSD maybe in latest version whether they have included, but in old version because EBSD very recently, I think EBSD also might have been included in the updated version. EBSD also is microstructure only, grain size, grain distribution, phases, how to interpret phases, and there are many things. Microstructure is like ocean. If I'm having one precipitate, if externally some 0.005% any additional alloying element, if I am having with that matrix, again it will change the precipitate morphology, size, distribution, orientation. The nature itself will get changed. Okay, so like that, especially one of the aluminum alloy, uh, iron is in iron is it cannot be removed completely from aluminum. Always it will be there with aluminum, iron, aluminum inclusions or precipitates you can see in any aluminum alloys. Okay, if you add something, uh, in nature it will present in the form of skeleton. If I am adding additional alloying element, the skeleton shape will change. Like a tree branches, it will be looking. Again, broken branches it will show. And if I am adding another thing, the branches itself, if you bend how it looks, it will look. So people named it as Chinese script. It will be looking like a Chinese script. So like that, the morphology, it will keep on change if I am adding any extra element into it. All the information you can get from that metallography handbook. So it will be really useful. Someone really wants to get into the microstructure studies.
I think there is one question in the chat box from Rayappa Srinivasji.
Yeah,
Some specimen polishing facility, is it available at IIT Dharwad for powder compacts?
yes, we have. Powder compacts means, have you sintered it or just it is in the compact form? It is in the green form. A few things I missed to cover also. Yeah, I would have included this powder part also. Yesterday also someone mentioned the powder.
Madam, it is sintered compacts only, madam.
Okay, if already in the sintered condition, it is
Yes.
easy. How big your sample is?
Madam, it is 10 diameter and 20 height.
Okay, if you want to keep the 20 height as it is,
No, madam, height can be reduced, no problem. But only the thing is, I need to for microstructure analysis is required.
okay,
It
see,
is
yeah, we
spark
can.
plasma sintered, madam. It is sintered by using spark plasma sintering.
Okay, so the metallic, the powder compacted or sintered product, again the sample preparation, you can follow the same procedure what we are doing for the regular bulk material.
Yes,
Okay,
yes, madam.
so need not to worry. Only thing, if your compaction is not happening properly, you may have the porosity at the interface, right? So this
Yes,
paper
yes,
polishing, the silica carbide, other things should not go sit into the gap wherever it is. You have
yes,
to
yes, yes.
clean thoroughly before taking further analysis. Because all the features will be seen in the our microscope will reveal everything, whatever is there. Either it is a dust or anything.
Madam,
So
it is
microscope won't bother.
electro
Yes.
electro polish or you're doing normal polish, madam? Emery paper.
Emery paper polishing only we are doing. Even electro
Okay,
polishing facility also we are having. Yeah,
okay,
that
okay,
time is to include. Yeah, there is another technique other than manual. We can do electro polishing also, right?
okay, okay,
Both the
madam. Thank you.
facilities we are having. Yes.
Okay, madam. Thank you.
Thank you. Thank you.
Any more questions? Any more questions? Yeah. So I thank Anbu Madam for very interesting and very useful presentation. Few people were asking for recorded sessions. That says it all.
Okay.
So we will be uploading all the sessions on our institute website. So it will be available throughout for years to come. And thanks a lot, madam, for enlightening session. And now we are floating the feedback form, attendance come feedback form in the chat box. Please, participants are requested to fill it. Please fill the feedback form.
Time is 10 minutes. You can take maximum 10 minutes.
10.
After that, it will be deactivated.
Yes.
Sorry, Professor Vinayak, I lost the connection in between. You were about to thank. We didn't say thanks.
Yeah.
A lot for
Thank,
having me. Yeah, it's really good experience.
yeah, and we would like to have you for more number of such sessions and the individual such characterization details. If, such methods can be spoken in details. We will be inviting you for future sessions also, madam.
Sure, sure. Yeah, you're welcome.
Uh, yeah, madam.
Uh,
Thanks a lot.
you're you like to take my consent or you are giving me the information that you will come back
Yeah.
to me?
Consent also. We wish you to bring on board for future sessions.
Okay.
So,
So we have only tomorrow on Saturday, right? So if you want any
uh,
additional session on
y-
Saturday, I'm
yeah,
fine.
Additional if is there, definitely on Saturday possibility is there. We will.
Okay.
I'll get back to you by tomorrow.
Yeah. Whatever I missed to include today, some of the
Yeah.
micro tensile other things. If you like to listen or hear from me, just you give me the titles and share with me, so we can join or meet again on Saturday,
Yeah.
or in some other event also. Anything is fine, whatever is
Yes.
required at this point. I'm happy to deliver.
Yeah. And few were asking your email ID. I think madam's email ID is available on the website. And,
Yeah, in IIT Dharwad website, the faculty link, you can click the faculty link on the top. My name is starting from the alphabet A, so you can find me in the beginning.
thank you, madam.
Yeah, thank you, Professor. Yes.